Hello everyone, welcome to the last part of this video series. Today, in this video, we are going to talk about the manual design process. Also, we will discuss the data visualizations inside Ekahau and see how we could interpret them. Let's go to Ekahau. So this is actually the file that we used in order to design Wi-Fi by using the AutoPlanner tool. It's the same file, the same design, except I actually fixed some ill-drawn or placed walls, okay? Also, I have added some attenuation areas like this one. And what else I have done? Yeah, I have added an exclusion area in this location and this location. This is because it represents actually an area between two walls. So I didn't want to include it in our design. Usually, once you are working on a real project, you have to verify with your customer about every inclusion and exclusion area you're going to add to your software. Anyhow, for the sake of our demo, I have excluded this. Now, we are going to start the design process. Let me first remove the exclusion areas as well as the walls in order not to mess with them. We are going now to select our access point. I'll start placing them. Then we can see how this process develops. So in order to select your access points, you have to click on this icon and we will choose Cisco Catalyst 9120 with internal antenna. Now, I have selected the first access point. I'll start usually from any corner. So I'll start placing the access point here. Now let's stop. Before you move on placing your access points on the map, you have to actually try to check the access point settings. So let's rename this to be AP1, and our access point TX power and channels should be actually checked. So since we are designing for, let's say, a high density area, especially in the auditorium, I would start with lower TX power. So here I'll start with 5 dBm plus 11 dBm for 5 gigahertz. Also, if you remember, our ceiling heights are 3 meters for the offices area and 10 meters for the hall. So we will start with 3, and then once we get into designing the hall, we will manually change the heights for each access point. So now we will use the internal antenna, which settings I need to take care of. That's it. Okay, so we have fixed this access point. You see the coverage got reduced because we lowered the power. So now let's get back to our access point of the same model. We will start placing the access points. Oh, by mistake, I have placed the access point on the wrong location. Control Z. Okay. Let's move on. Now, you need to place your access points in location where you find best in order to avoid coverage holes. Maybe it won't be clear in the offices, but we will show that case in the hall. Okay, let's place one here. That sounds good. To the other room. This one is excluded. If we place access point inside, since we have an exclusion area, it won't show anything inside that. Let's remove it. Then let's place one here, and then let's get back maybe here. We have a coverage hole. Now we will fix that. Let's put one here, and another one in this room, another one in this room, or in the corridor. We have a decent bleeding from this one to this one. So let's see how we can manipulate that. Okay, let's focus on this part. So basically, maybe if we move this just a little bit, we cover the hole. What else? Let's try to get this here. That's fine. Maybe I can do this also here. I don't think I can move it further. That would be good. What about this? Maybe we need to put it in this location. And in order to cover this area, maybe we can have this in this location. So let's try to shift this a little bit. It doesn't work because, okay, so this one would be perfect. What about this one? Yeah, that sounds better. So this is the process of placing access point. Now, one thing I encountered in Ekahau, when you add the walls, for example, let's see if we delete this wall, what happens? You see, the previously uncovered areas actually got covered now. But if you return the wall back, then it doesn't actually show this area, this small area, and this small area as covered. So why is that? I think, but I'm not sure honestly, it might be because that Ekahau performs averaging between this point, this point, this point, this point, this point, perform such a kind of averaging function between uh, all points around a certain point. And then because we don't have, let's say, nice coverage inside this backstage area, let's call it, which I already excluded, then the wall actually causes this area to be uncovered. This is something that I could think of, but I'm not totally sure. Okay, let's proceed with this one with the AP placement quickly. By the way, the AP placement process just takes time. I'll not do it for all locations. I'll just show you how you can place your access points in order to maybe try to cover the areas of interest. So we have some coverage holes. Maybe we can try to fix them like this. This one, it's not recommended to move it down. The distance sounds to be between each AP of around 11 meters. Let's see this one. This one has longer, 11, 13. That's good. What about this and this? Okay. So this is the AP placement that we will settle for these two areas. Now let's move to the whole area. We agreed that we will be using the access point, the same version of the hardware model of the Catalyst 9120, but this one will be with external antenna, and we will use this model. So we will place one randomly here, and as you can see, we have strange coverage. So if I put one here, I can cover the whole uh, hole. But that's not the right thing that you would do. In the first place, you need to actually edit the access point. So the access point is wall mounted. So the coverage pattern, as you can see, it's pointing into this direction. Furthermore, the access point actually is on this height. So let's just modify this to 10 just to see what will happen. Actually, nothing has changed. And let's change it to wall mount. You see, now it's pointing down. Since this is, let's say, a more dense or denser area, okay, we are going to lower the power. So I'll start with 2 here and with 8 dB as compared with the internal antenna access point. Okay, so I think we will actually change the TX power of this AP because usually we would consider from 30 to 40, let's say, the client device per AP, and this one appears to be covering more chairs, which means more users or devices per AP. So in order to force clients to be associated to a certain access point, we have to lower the power. So let's do that on 5. That sounds better, but let's see what we are going to do. Let's check the, oh, the 2.4 is even higher. Let's try to lower that first. I think this is the lowest TX power we have. Again, the antenna has 13 dBi, which will be added to this value. So we will have a total of 14 dBm transmitted from this antenna. Okay, so let's try to go with this. This is the minimum we can, let's say, lower the power by using the 1 dBm. Let's design for 5 gigahertz. Okay, so for 5 gigahertz, let's try 2. Let's see what will happen. Okay, that's better. That seems to be better. Okay, good. What is the height of the access point before we assume? We didn't change the height. Now, you will notice if I raise it to 10, the coverage pattern will increase. So that's normal because the angle that this access point is used to direct coverage, let's say, I think it's around 55 degree or something like that. So as we move it up, it will increase the area that it covers. So let's try to lower that to 1 and see what we can do. Okay, that's the minimum that we could achieve. Okay, now we will start placing the access points. Let's put the AP here. And the same issue actually is encountered on the borders of this hole. As you can see, if I delete this, it will be covering everything. Even if I move this AP here, you will still see actually coverage holes. So that is, I think, related to Ekahau averaging. Anyhow, we will not bother about this. Now, we will start placing the access points. I just want to remind you that the height will differ as we move actually from this location to this location. So we need to consider this because you noticed that the coverage pattern gets changed as we change the height. So let's proceed with AP placement. Now you can place them like this in order to provide the coverage. So we will have an access point here. Now we will put an access point here, an access point here, an access point here, just to get the overlap. The overlap requires to be fixed, but before that, we need to decide the access point height. So for example, I'll consider everything. Oops, I messed with the wall. Let's just turn it back and let's hide the walls. We'll assume anything on this location would be on 10 meters. This one will be on 8. This is just an assumption. Usually you have to go on site and collect that or let the customer provide this information. Let's go for 6 meters. Coverage would change for sure. Let's go with 5. It is multiple access points. So this is 5 meters. Now we started to see coverage holes, and we'll actually use 4 meters here. And now you should actually start fixing the coverage hole. So I think this one could be moved, and this one should be added here. Maybe we need to add another AP in this location. Copy paste access points. And that's it. You should do the same in order to cover actually all the coverage holes. I don't want to waste your time, guys. I have another file that I have prepared before starting this video where I have the proper access point placement. Okay, so this is the layout, and let me show you the access points I placed. Let's produce the signal strength visualization. As you can see, I placed access points to try to cover most of the coverage holes, but it's still not perfect because we still have some uncovered areas like this one, like this, and this, etc. I won't bother about this because it's still a demo. I won't spend that much time trying to fix things for now, but you have to do it when you work on real project. Also, if you remember, we provided justification for the areas like this. If we delete the wall, then it gets covered. These areas actually get covered. So we won't bother also about this. It might be related to the Ekahau averaging that I explained, or it might be any other issues that I'm not aware of. Anyhow, for now, let's start with the visualizations. As you can see, most Ekahau or all Ekahau visualization options are listed here. And you can select to view that either for all your access points or a selected access point. For the other access point options and all access points, we will not refer to them for this demo, maybe in future demos. We will take care about my access points and selected access point. We can produce visualizations for either 5 gigahertz or 2.4 or both of them. Moreover, you can find options related to each visualization type. Let's try to check them one by one. Airtime utilization. Oh, everything is red. What's that? I think COVID-19 has just passed by this area. Just kidding, guys. I hope the situation around the world gets better and we get rid of this lockdown. Let's get back to our demo. So basically, if we get back to empty, I figured out what's the issue. We have all access points running on the same channel. This is referred to as single channel architecture. It produces good coverage, but at the same time, it's not good for capacity. We will not rely on such a kind of architectures, actually. We have to move into multiple channel architectures. So you can change the access point channel running on each radius either by editing the access point and doing that manually, or you could actually take care of the advantages presented by the automatic channel planning feature in Ekahau. You can actually ask this tool to optimize channel assignment for your access points or a single selected access point. You can do that for both bands or either one of them. You can ask Ekahau to figure out what best access points to disable the 2.4 radio. Why actually we do that? Because as you know, 2.4 transmissions travel far more than the 5 gigahertz. That's because of the frequency. And based on this fact, the 2.4 coverage cell will be bigger than the 5 gigahertz. Thus, it will cover more areas. So, in order to fix channel interference, usually we disable 2.4 or some of the 2.4 radios within the environment. So we can rely on Ekahau to do that for us using this option. Now, the channels that I would like to use in the 2.4 is 1, 6, and 11. For the 5 gigahertz, I will use all available channels for now, but bear in mind that you have to do, you don't have to do this, but you have to select the channels available per each country regulatory, I would say, regulatory code or the available channels for each country. As you can see, you can Google that, you can go and check what are the available 5 gigahertz channels in each country. For now, as I said, I'll stick with all available channels in our demo. Okay, let's create the plan. And as you can see, let's see what's going to change. Yeah, this one is on 11 and 108, 6 and 64, 140, 11, 136, etc. Also, we can see that for these access points and the others, actually, Ekahau decided to disable those radios. Okay, so before we check the visualizations, I wanted to actually show one thing. Okay, let's leave it. Let's leave it. Let's proceed with the visualization for now. So if we get back to the airtime utilization, in the first place, what is airtime utilization? Well, actually, each access point we have placed has its own available airtime that or by which it actually serves users. In theory, the airtime utilization refer or has to do with the medium contention and back-off process in the 802.11. So each station has to compete for medium access in order to get the chance to transmit, which is referred to as TX-op or transmit opportunity. So usually the higher, or let's say it like this, usually the lower the data rate for the associated clients in each AP, then the longer these clients take in order to complete the ongoing transmission. So this will lead to actually having higher airtime utilization in our cell, which will be in the end interpreted as bad user experience or bad Wi-Fi connection. As we can see, everything appears to be between 0 and 65 channel utilizations, as we are able to see, let's say, the coloring scheme green in most of our environments. This is true for 5 gigahertz only. So let's see the percentage. And this is nice statistical visualization that you can refer to and share with your customer in your design. So we have around 94% of areas that are healthy in terms of airtime utilization, but let's go to 2.4. Now this one is infected with COVID-19. Actually, sometimes because of the less options that are available to select from in terms of channels in the 2.4, that actually increases the channel utilization in 2.4. Let's try to see what actually failed in this area. So you can see this tooltip. It shows 100% airtime utilization for voice, and it seems that 70% of BYODs will have or will consume the airtime in this area. And yeah, as you can see, this is just a tooltip showing, let's say, a prediction for the environment in terms of airtime utilization and according to the capacity and coverage requirements that we have defined previously for each area. What about this location? Well, that differs a little bit. Anyhow, so that's it about the airtime utilization. What else? Associated access point. So what does it mean in the first place? It actually refers to a predicted association. So Ekahau actually tries to predict the location or each location and which access point could be covering that location. So let's hover on this location. It shows that if I'm a client and standing there, then I'll be associated to AP19, so AP19 will be this one. If I hover on this location, then 21, etc. So I think that's super easy to understand. We don't have statistical views for this one, but same case goes for 5 gigahertz. No, we didn't perform site survey, so we will stick with the predicted association. And that's it about this visualization. Next, capacity, which is clients per AP. Now, as you can see from the coloring scheme, everything appears to be meeting the requirements in 5 gigahertz from 0 up to 35, let's say. So we're good. So it's saying from 0 to 20 clients, most of the areas will be having this number of access points, and the remaining 6% will be between 20 and 40. Let's go to 2.4. That actually changes a little bit. I want to do something actually. If you remember, we have defined capacity for each area. So let's edit this area and let's have 2000, let's say 630 clients or device in this area. Let's see what changes for the visualizations as we actually increases the number of clients. So you see, we still have, now we are going to locations where we increase the capacity per AP. So for example, in this location, in this AP, we will have around 229 clients or device per AP, which is not healthy. Let's see 5 gigahertz. Situation is better in 5 gigahertz because we still have multiple channels to select from. So I just want to showcase this for you guys to understand. Let's revert back to the original requirements. So the synopsis here is that the more stations you add to the environment, the denser the environment will be. And actually that will affect the available airtime that we already checked based on each client capabilities that you add. Okay, what's next? Capacity health. So in 5 gigahertz, we have a green light on all these areas, but Ekahau expects a failure in this. But again, we can't say that this because of the number of clients. Actually, we need to hover over this one and we see the culprit, which is the airtime utilization is higher. So capacity is tightly connected with the airtime, because if you don't have airtime, then you cannot add more clients and have more capacity in your environment. So these two things are tightly connected to one another. Let's check 2.4, which is failing here. Why? Because again, airtime utilization is high in these areas, so we are expected to fail. Next, so we have all access points running on 20 megahertz channel. So that's easy to understand. Let's check the channel coverage. This is somehow related to the same as the associated access points. So Ekahau here just assign color code for each channel, and you can check that just in one available, let's say, layout. That could be helpful when you are troubleshooting maybe the CCI, which we will touch base later on. Channel interference. Okay, so what's channel interference? This actually refers to two types of interference. They are known co-channel interference and adjacent channel interference. So you can actually select to view actually one of them or both of them. We don't have adjacent channel interference for sure. Okay, so what is the co-channel interference? It is actually a situation where you have two or more access points running on the same channel, but they are close to one another in a way that it causes channel contention or medium access contention, and deferral for the communication within each cell and all stations associated to each cell. So, CCI, the increased CCI causes performance issues in the environment. We have actually defined in our project requirements that we don't want to see more than 2 access points running on the same channels that are able to hear one another on this value. We can play with this one, but this is the main, or these are the main coverage requirements that we have defined. We will stick with those. So we can see that we are not facing any issues here and in the lower part of this area. But this concert hall, it's an open area, so it's expected to have that. And again, we are still within the coverage requirements. What else we need to check? Let's check. Yeah, we are on 5 gigahertz. Let's check 2.4. 2.4, again, since we have 3 channels, then we don't have that much or that many options to select from. So we will have more CCI. Data rate. This is the theoretical data rate that you are expected to get per the signal strength that you actually connected to. So this is theoretical one. We will touch base on the throughput and other visualization, but we can see we have good data rate here and also in the upper layer or the upper layout. In the middle, we can see it's around 120 or 140 megabit per second. Same case for 2.4. Let's move to Jitter, and Jitter is something we are not able to actually talk about in this demo because it requires real-time measurements on site where you will use your laptop and an iPerf server to provide as, let's say, such a communication in order to measure the jitter and packet loss, round trip time. Yeah, these 3 visualizations. We will not be able to actually explain because they require to be on site with some real measurements. Network health. Well, now this is very important visualization. Actually, it simply marks each area within the layout with either a pass, green, or a fail, red. After it has actually evaluated all our coverage and capacity requirements that we have defined here and in each area, then actually it provides this visualization, but it doesn't provide you with why or the reason behind that. You have to investigate that. The good thing is that Ekahau added this visualization that we will check, which is network issues, which actually provide the reason behind this failure and pass. So before we move to the reasons, let's see the 2.4. We have it failing everywhere. Now this one is infected with COVID-19. Okay. What else we can see here? There are not that many options that we can check in this option. We have in 2.4, or sorry, in 5 gigahertz, around 87% of our layout passing the requirements. We will exclude these and these because they are the borders that we talked about. So it could reach to 90%. So that's good in terms of design. The 2.4 is the other way around. Okay, now What are the reasons behind the pass and the failure? Mainly in 5 gigahertz, we have two main reasons. The primary coverage, which is the signal strength, and the secondary coverage, which is STR or signal strength 2. So signal strength, it's, as you know, uh, the signal coming from the access point. But what is the secondary coverage? As you know, in some designs, we might be required to cover a certain room by 2 access points or provide double coverage. So we can see this, for example, in this room. If I want to fix this secondary coverage issue in this room or this room, I can simply go ahead and add 1 access point. You will see that the orange visualization or the orange color disappeared because now we are meeting. We are covering this area with 2 cells from 2 access points. For our design, I won't care about this. I will consider it a luxury if you have a secondary coverage. Our customer didn't request that, and it's not required in these areas. So again, I will not care about this. So the 5 gigahertz seems to be healthy to me, around 95% if we disregard the secondary coverage and the primary coverage areas like this. But 2.4, we have actually another added culprit about the failures in this area, which is the pink color. Okay, so 2.4 is suffering from ch.I, which is channel interference, which is the CCI that we talked about. So if we hover in this location, we can see we have 7 access points, okay, are heard on the same channel on this location, while in our requirements we have defined it to be a maximum of 2. So that is a complete failure. In order to fix this, we already asked Ekahau to disable 2.4 radios. You can either live with this or try to disable more radios in order to fix, but whatever you disable, it won't get fixed because this is the nature of 2.4. And bear in mind, the more you disable, the less coverage you will provide in this area. So if we try to disable this, for example, let's go with this. And let's disable this. Disable this. We're still in healthy coverage. Let's disable this. We might be required to do that for every other access point. Let's disable this. We are still in a good coverage. Let's get back. I won't go through all of them. But again, even after the disable of multiple 2.4 radios, we still didn't get the opportunity to produce or to move to any better situation in 2.4. So we will have to live with that. Next, noise. Actually, this refers to the noise floor. I don't rely on this one in predictive survey because it will always be around NIG 90 or NIG 95. You have to go on site and measure the actual noise floor inside that layout, that floor actually. It refers to the noise floor, as we said, and the higher the noise floor in your environment, the less chance that we can maintain the signal to noise ratio, and thus we will not have a good quality in terms of wireless connection between the wireless client and the access point because we couldn't maintain the SNR. So simply, we will check the SNR in another visualization. Number of access points, this actually refers to the number of audible access points in each location. So if we hover here, we can see we are able to hear 14 access points on different channels, not on the same channel. That could cause some issues for some sticky clients. What else? Same case for 2.4. Packet loss, we're not able to explain, and round trip time. Signal strength, we have already touched base on that. 2.4 and 5 gigahertz. Actually, you can play with the opacity. So if you can see how it changes, I usually leave it on the default. What else? Secondary coverage, this is the one that we talked about, which is the secondary access point that will cover each area. And tertiary coverage, this one will be used for the location tracking. Coverage planning, let's discuss this in future videos. This is the SNR, and we can see we have decent SNR that is meeting the requirements in all areas, actually. Let's get rid of the radios. This is in 5 gigahertz, 2.4, same case. We will stick with predicted, not measured, because we didn't go on site. What else? Spectrum channel power, same case, will not be able to optimize that. You need actually a spectrum analyzer while you are doing a real survey in order to have this one. Same case, I think, for channel utilization, for the real channel utilization. Throughput. So throughput will be different from the data rate. Data rate is the, let's say, theoretical speed that you could achieve once you are connected to an access point with, for example, NIC 70. You can be associated with MCS, for example, 4, let's say, or 5, but the actual throughput will be half that value, because usually the throughput equal half the presented or the data rate on which the client is connected to. So if you are connected on, let's check this location, let's see what Ekahau actually provide us. So I can say BYOD devices are connected to 65 megabit per second actual throughput, but if I go to data rate and hover on the same location, you'd see that BYOD devices, it's showing the same. Okay, maybe we need to select another location. Let's try to go for this one, for example. Let's select this chair. So data rate here showing 65, it didn't change. Let me see the actual throughput that Ekahau could present here. Okay, now it's showing a max of 55.4. This is the maximum you can attain here. But it wasn't available here. Okay, so you understand the difference. The maximum that Ekahau calculated, but usually you need to consider in your capacity that if you are connected into 100 megabit per second as data rate, then the actual throughput could be between 50 to 70% of that value. Interferers, I think this is the last one that we are going to talk about. So we cannot actually present this here, but usually once you go on site and you have surveyed the site, you might encounter or you might pass by a camera or microwave oven or let's say cordless phone that that runs let's say on a certain frequency, and this one will be detected and placed on your map. Okay, so what else we need to check? Difference in signal strength. This requires actually on-site survey and two paths where you can differentiate between them. Bluetooth, we will discuss this maybe in later videos when we check BLEs. And that's it. Actually, that's all I have for now. I hope you guys enjoyed the content I have presented. Actually, I have tried to go through one scenario from A to Z for you guys to try to picture or imagine how it actually could be when designing, let's say, one when you're performing design for one layout. You could always go to this site. Let me actually show it to you, dwgmodels.com. You can search here for AutoCAD layouts. You can download them for free. You can import them to your site survey software and try to practice. It will be a good opportunity for you to repeat actually what I have done in these videos in order to fully understand, because the best knowledge comes from practice. And finally, I hope this was informative for you guys. I would love to hear from you. If you have any question, please feel free to write them in the comments in the YouTube channel, or you can always reach out to me on Twitter on this handle, Mahmoud Ashur. And I would like to thank you for watching. Please subscribe to the channel and stay tuned for future videos. Goodbye for now.